new topic that is stationary waves. And in today's topic, since we are beginning the stationary waves, we will see the introduction part of the stationary waves, and then the very first article, that is analytical treatment of the stationary waves, where the other end of the pipe is closed or other end of the string is fixed. So let us start the today's lecture. Okay, so let us have some introduction about the stationary waves. So the wave, stationary waves, the topic is a little bit introduced to you in the standard 12th or might be in standard 11th, and you can recall your memory by looking at the figure that has been shown here, where the stationary waves are formed by a tuning fork, by connecting a rope string to a tuning fork where weight is attached to other end of the string, which is passing over the pulley. Okay, and when this tuning fork vibrating, the specific wave pattern has been produced where there is no displacement at few points, and those are called as nodes. And in between any two nodes, there is a point where the displacement is maximum, and that is called as antinode. So this is about the stationary wave. Now, question is how these stationary waves are formed. The stationary waves are formed when two similar and equal wave trends, similar in the sense they have same frequency, that means they have same time period, same wavelength, but traveling in the opposite direction, but with the same velocities. Okay, when such type of two waves, okay, superpose over each other, they give rise to a standing wave pattern or stationary wave pattern, where the particles are either at the nodes where displacement is zero, or at the normal positions or at the maximum positions. Those are called as antinodes. Okay. Now the question is why these waves are called as stationary. Let us explain the formation of stationary wave pattern in this figure, and you will find that this is the wave that has been generated from the prong of the tuning fork at point P, so shown by the solid line. So the wave is generated, and from the closed end, this wave is reflected and reflected back in the opposite direction. So the wave has the waves, the wave incident and the wave reflected from the closed end, both have the same type of, same frequency, same wavelength. That means, okay, similar type of wave trends, but they are moving in the opposite directions. They are moving in the opposite directions. So that is okay. So since they are moving in the opposite directions, similar wave trends moving in the opposite direction, one is traveling in forward direction, that is the incident wave shown by solid line, and other is traveling exactly in the opposite direction, that is the wave reflected from the closed end where the pulley is there. Okay, so these two waves having equal velocity but traveling in opposite direction gives rise to a pattern, okay, where the particles are not in the motion, they are stationary. Okay, and in this stationary pattern we will find that at certain points the displacement performed by the particles is zero, and these are called as nodes, and in between the nodes there is a point where the displacement is maximum, and that is called as antinodes. Okay, such type of pattern is called as stationary wave. Now the question is why the pattern is known as stationary. Why the pattern is called as stationary? This is because the particles are at their own positions, vibrating at their own positions. Okay, for example, if the particles at the points nodes, they are vibrating, they are at zero displacement. Okay, and in going from node to antinode, their displacement is increasing, and when they are at antinode, their displacement is maximum. Okay, but important one is that, okay, there is no transfer of energy. Okay, there is no transfer of energy since the particles are stationary. Okay, since there is no transmission of energy. Okay, there is no flow of energy along the waves. Just like in case of the what you say progressive waves, there is transfer of energy. There is no transfer of particle, but there is transfer of energy. But in this stationary wave pattern, there is no transfer of energy. Okay, so therefore these are called as stationary wave. In stationary wave pattern, the whole medium is found to be divided into two types of segments. Okay, the segments are exactly in the opposite direction. Now, if you are looking at this segment, the particles are vibrating in the downward motion. Now, if you are looking at this segment here, the particles are vibrating in the upward motion. So, the phase of the consequent segments are exactly opposite to each other. Okay, so this is the important thing, that whole medium is divided into different segments, and particles in a segment are in the consecutive segments are in the exactly in the opposite phase. Okay, so there are certain points where the displacement is zero, and these points are called as nodes. And in between these nodes, exactly at the middle, we have the point where the displacement is maximum, and these points are called as antinodes. So, in this way, we have the exact displacement points, those are called as nodes and antinodes. For nodes, the displacement is zero, and for antinodes, the displacement is maximum. So this is about the stationary wave pattern or standing wave pattern. Now, let us look at a few more characteristics. There are two types of stationary waves depending upon the component waves. Okay, these stationary waves are uh, transverse stationary vibrations and longitudinal stationary vibrations. Okay, as it is shown here in this slide, if the component waves are transverse waves, and the best example of transverse waves is the light waves, where the whole wave is divided into alternate crest and troughs. Okay. Now the example that I have shown to you in the previous, so here this is a transverse wave that has been produced along a vibrating string. Vibrating string. So this is a transverse wave where it is a trough and it is the crest. Okay. Now when such type of transverse waves, two components of transverse waves are utilized to produce the stationary wave. The stationary wave pattern is called as transverse stationary wave. Okay. Now, on the other hand, if the component waves are longitudinal waves, and the best example of longitudinal wave is the is the sound wave, where whole medium is divided into alternate compressions and rarefactions. Okay, and the best example is organ pipe, what we call in Marathi as basri. Okay, these stationary waves set up in the vibrating column of the air in an organ pipe are the best example of the longitudinal stationary waves. Okay, so in this way there are two types of stationary waves: longitudinal stationary waves and transverse stationary waves. The example of transverse stationary waves, as we have explained in the previous slide, that is the waves along the vibrating string, and example of a longitudinal stationary wave are the waves produced in the vibrating column of the air in an organ pipe. A lot of examples are there of organ pipe. The best one is the basri, what we call it in Marathi. Okay, so these are the two examples, two types of stationary waves. Now let us look at the analytical treatment of the stationary waves. Let me explain first of all that there may be two types of stationary wave patterns. One that has been shown in this figure, where the one end of the organ pipe, one end of the passy, one end of the organ pipe, or one end is closed, one end of the string is fixed, or the organ pipe is one end of the organ pipe is closed. This is called as closed ends. So this is one thing. And another example may be there where the string is not fixed, Okay, it is just free to vibrate, and the other end of the bassri, another end of the organ pipe is not closed one. So these are two examples. So open end and closed end, and at the first we will see the closed example of closed end organ pipe or the string fixed at the organ end. So we are familiar with the vibration or the displacement of the particle for forming SHM, and that is equal to, that is given by y equal to a sine 2 pi by lambda Vt minus x, where the wave trend, wave progressive wave is supposed to traveling or progressing along x direction, and the particle is vibrating along y direction, perpendicular to direction of propagation of the wave, and the distance x of the particle in the medium is measured from origin in the direction of propagation of the wave. Okay, where x distance is measured from the origin in the direction of propagation of the wave. Now, here the wave is supposed to be originated from point A, as it is shown by the solid curve indicated as incident wave, and it moved to the interface or the closed end of the organ pipe or the fixed end of the vibrating string. Okay, and from, okay, now if we measure the distance from point A, from where the wave has been originated and originating towards this direction, then the distance will be the equation will be this, where the x will occur as a minus x. Okay. Now, if we are measuring, the wave is propagating in this direction, okay, in the forward direction, for example, and we are measuring the distance from the interface, xy interface from point O, okay, that means exactly in the opposite direction, then what will be the magnitude of x? It will be exactly opposite to this, okay. So this is plus x, okay, where that equation will be y1 equal to a sine 2 pi by lambda Vt plus x, and this we consider as the expression for the incident wave. Only the thing we have made is, for our convenience, we have measured the distance of a particle point P, okay, exactly in the direction opposite to the direction of propagation. The direction of propagation from is from point A to O, and we have measured distance from O to A, exactly opposite direction. So that's why the sign of x has been changed, reversed from minus x to plus x. So this will be considered as the expression for the incident wave. Okay, only remember that sign is reversed because we are measuring the distance x exactly in the opposite direction to that of the direction of the progression of the wave. Okay, so now when the wave is reflected, okay, as it is shown by the dotted line, okay, so this is the incident wave, and from point O, the closed end of the pipe or the fixed end of the string, the wave is reflected back, and it is shown by the dotted curve. So this is the reflected wave. Now when the wave is reflected, there comes a phase change of pi radians or 180 degree. And if we introduce this phase change in the original wave is a sine 2 pi by lambda into Vt minus x, and a phase change of pi is introduced. So this is just a theta plus pi, and sine theta plus pi is what? Minus sine theta. So it becomes minus a sine 2 pi by lambda Vt minus x. Now this is the expression for the reflected wave. Expression for the reflected wave. Now, important thing is that two things we have to remember. That is about the sign here, that is negative sign, and the negative sign is because the phase change of pi radian or 180 degree that has been occurred. And here the sign of the x has not been changed, and that is because we are measuring the distance x in the direction, okay, that has been, okay, that has been in the direction of progression of the reflected. Look here, the wave is progressing in this direction from O to A, and we are measuring the distance in the same direction. So in that situation, there is a negative sign, original equation. But since there is a change of path, so negative sign is here. Okay. So these two wave trends along the medium, okay, the solid wave and solid incident wave and the reflected dotted wave. These two wave trends, okay, are there in the medium, which have same wavelength lambda, okay, that means same period and frequency, and which have same amplitude a here, okay, and which are traveling exactly in the opposite direction. The progressive wave is traveling from A to O, while the incident wave is traveling from A to O, and the reflected wave is traveling from O to A, traveling with velocity v exactly in the opposite direction. So these two waves gives rise to a stationary wave pattern in the organ point. Okay, the superposition of these two waves traveling the similar waves, similar in the sense they have same wavelength, they have same amplitude, that means same frequency and period as well. Okay, and but traveling exactly in the opposite direction, and such waves gives rise to a stationary wave pattern, as we have seen in the very first slide. Now, let us treat it mathematically. Now, what will be the resultant displacement? That will be y equal to y1 plus y2. So this is y1 and this is y2. Okay. Now, if we solve this equation, okay, it will be simply sine a plus b minus sine a minus b, and that has been solved here, and we will find that sine a plus b means sine a cos b plus cos a sine b, and again here sine a minus b sine a cos b cos a sine b, and the resultant is 2 cos a sine b. Since the factor common, that is sine a cos b sine a cos b cancelled out, and cos a sine b plus cos a sine b gives rise to 2 cos a sine b. Now what is a here? A here is 2 pi vt by lambda, and what is b here? That is 2 pi x by lambda. Now if we put here, we will find that it is 2 pi vt by lambda for cos, that means, and 2 pi x by lambda for sine. So this will be the equation, and the final equation will be 2a sine 2 pi x by lambda cos 2 pi vt by lambda. Let us call it as equation number 3. Now, what about this equation? If you are looking at this equation, you will find that again the velocity is v, the wavelength is again the same lambda, okay, but what has been changed here? The change is in the amplitude, and the amplitude is now 2a sine 2 pi x by lambda. That means amplitude is changing with the position, sinusoidally, changing sinusoidally with the position. And let me recall the stationary wave here in the first slide. Okay, as I have told you, here amplitude is 0, and it has been increasing sinusoidally, and it is maximum here. Okay, at the position of antinode, it is decreasing sinusoidally, and becomes 0 at the position of node, then increasing. So from antinode to node, decreasing trend. From node to antinode, it is increasing trend, and it is decreasing and increasing with the specific period, and that is the period of the original component wave. Okay, so and it has the wavelength that is equal to the wavelength of the original wave. Okay, so amplitude is varying sinusoidally. Amplitude is varying sinusoidally. So that is the important thing, and the period, frequency, wavelength, velocity, those are remaining. Say, let us look at the, what you say, dy by dx. And what is dy by dx? That is we call as slope of the curve, or the strain that has been produced, or compression per, okay, compression that has been produced in the medium due to the wave. And what is that? That will be dy by dx. That means we have to differentiate equation 3 with respect to x, and differentiating this with respect to x. So x is here with sine. So sine 2 pi x by lambda becomes cos 2 pi x by lambda, and component of that is constant component with x, that is 2 pi by lambda. So that is out of here, and it will be simply 4 pi a by lambda cos 2 pi x by lambda cos 2 pi bt by lambda, equation 4. It represents the compression. Okay, so important thing is that here it is the cosine function, and that will result in some interesting thing. Now, what about the velocity? Velocity can be obtained simply by differentiating this equation 3 with respect to time. Now, here it is the component t is there with respect to t. That means this cosine become sine, and that is better, minus sine 2 pi vt by lambda. And only the thing is that 2 pi v by lambda, this component will came outside, and we will have here, okay, as minus 4 pi av by lambda sine 2 pi by lambda sine 2 pi vt by lambda as the velocity. Okay, so we obtain displacement and velocity. Okay, now the important thing is that in displacement here both terms, in displacement sine term and cos term, position is sine term, time is cosine term, and in strain both are cosine term, while in case of velocity the position term is sine, and again the both terms are sine. Okay, now let us look at the changes with respect to position, how the changes took place with respect to the distance from the interface, xy interface. Okay, and if you are looking at the component, trigonometric function, okay, with respect to position, that is occurring with respect to position, there are two functions, that is sine 2 pi x by lambda and cos 2 pi x by lambda. Now we consider first of all as sine 2 pi x by lambda equal to 0. Okay, sine 2 pi x by lambda, it may change continually, and it can take the values from 0 to plus or minus 1, minus 1, 0, plus 1. These are variations in the sine theta. Okay, so we consider first of all theta. First of all sine function as 0. If we consider sine function as 0, the similar cosine function will be plus or minus 1. For example, it is sine 0, then what about cos? It will be plus 1. For example, if it is sine pi, it will be 0, and what about cos pi? It will be minus 1. So remember very well. Okay, so if sine function sine theta is 0, what about cos theta? It will be at its maximum extremities, that is plus 1 or minus 1. So if we consider sine theta, sine 2 pi x by lambda equal to 0, in this case, it will be cos 2 pi x by lambda, that will be plus or minus 1. Now look at equation 3 and equation 5. Equation 5 is here. If we put here 0, the velocity sine function as 0, velocity will be 0. And what about equation 3, that is here? If we put here, now here it is a cosine function. Okay, it will be, no, we are doing with position, so here it is again sine function. So displacement is 0. Displacement and velocity become 0. And what about here? The velocity. What about velocity? Sorry, what about the strain? Here it is cosine function, so plus or minus 1. So strain will be maximum. Displacement and velocity will be 0, and strain will be maximum. Let us look at here. So from 3 and equation 3 and 5, displacement and velocity both are 0. But from equation 4, it is clear that the strain is maximum. And where the strain is maximum? Strain is maximum where the displacement is 0, and these are the positions of nodal points or nodes. That means the points where function sine 2 pi x is 0, these represents the nodal points or nodes. Now, how will you find these positions? Okay, so since 2 pi x by lambda equal to sine 2 pi x by lambda is equal to 0, that means what about 2 pi x by lambda? Sine theta is 0 when theta is either equal to 0 or pi or 2 pi or 3 pi, 4 pi, 5 pi, etc. etc. That means when theta is equal to m pi, where m is an integer taking values 0, 1, 2, 3, and so on. Okay, so we have to equate 2 pi x by lambda, the angle of sine with respect to m pi, and here you will find that x equal to m lambda by 2, where m equal to 0, 1, 2, 3, and so on. So the positions of x where the nodes, these are m lambda by 2. For example, if m is equal to 0, what is this? This will be simply 0. If m equal to 1, what about the value? Lambda by 2. If m equal to 2, 2 lambda by 2, that means simply lambda. So in this way, 0 lambda by 2, lambda, 3 lambda by 2, 2 lambda by 2, 2 lambda, okay, etc., etc. All these are the nodes, okay. And important to note that at the interface where the reflection has been occurred, so at the closed end we have shown here in the what do you say diagram as the xy. So this is the interface xy, this is the closed end, okay. And here you will find that at this end, okay, that means at x equal to 0 we find a node, okay. Important one is that for closed end of the analytical case of the closed end stationary waves formed due to closed end, there is a node at the closed end, or there is a node at the xy interface or interface, since we obtained the position x equal to 0 of the node. Now, what is the distance between any two consecutive nodes? So it is lambda by 2 0, it is equal to lambda by 2 minus 0, it is equal to lambda by 2, 3 lambda by 2 minus lambda by 2. So the distance between any two consecutive nodes, that is equal to lambda by 2. So nodes are separated by distance lambda by 2. Now let us see the reverse thing. In initial condition, we have considered sin 2 pi x by lambda equal to 0. Now consider cos 2 pi x by lambda equal to 0. Now what will be sin? That will be plus or minus 1. And if we put here the values in equation 3 and 5, okay, so it is sin 2 pi x by lambda, and it is in equation 3 and 5. In equation 3 and 5, we have, okay, here it is equation 3. Sorry, equation 3 is repeated. So we consider this equation 3. In equation 3, if we put sign, so it will be plus or minus 1. That means displacement is maximum. So here it is a cosine. So cosine function is, we have considered 0. So strain is 0. Displacement is maximum. Strain is 0. And what about velocity? Velocity, again here it is a sine function, so maximum. So displacement and velocity are maximum and strain is 0. So strain is 0, displacement and velocity. Displacement is maximum, that means particles are at their amplitude position. So these are the positions of the antinodes. When cosine function is 0, we get the position of antinode. And how these positions are obtained? Simply, here cosine function is 0, therefore theta, angle theta is either equal to 0 or pi by 2 or 3 pi by 2 or 5 pi by 2. So this is what? Odd multiples of pi by 2. And how odd multiples of pi by 2 are obtained? If m is an integer, double the integer and add 1, you will find the odd multiple, odd number, okay. So it is 2m plus 1, okay, multiplied by pi 2, odd multiples of pi by 2 for m equal to 0, 1, 2, 3 and so. And if we solve here, we will find the value of x as equal to 2m plus 1 lambda by 4 for m equal to 0, 1, 2, 3. And now put here the values. You will find the positions of antinodes. Now if m equal to 0, so it will be simply equal to 0 plus 1. That means 1. That means lambda by 4. So lambda by 4 at distance of lambda by 4 from the interface, from the closed end, okay, you will find the first antinode. So first antinode is at the distance of lambda by 4, okay, from the closed interface. And where is the node? The node is at x equal to at the interface, and from that distance, at the distance of lambda by 4, there is antinode. So distance between node and consecutive antinode is lambda by 4, while distance between two nodes is lambda by 2. Okay, so this is the important. And what about the next one? Next one will be at m equal to 1. That means what? If we put here 1, it is 2 lambda by 4. That means lambda by 2. So in this way, the consecutive positions, okay, the consecutive positions we find here are lambda by 4, 3 lambda by 4, 5 lambda by 4, and so on. Again, you can find the distance between any two, that is equal to lambda by 2. So distance, they are separated by a distance of lambda by 2. What about positions with respect to time? Okay, if we put sine function sine 2 pi vt by lambda equal to 0, okay, you will find that now here one change we have to make, that we have to put v equal to n lambda. And by putting here in this way, you will find that n is equal to 1 by 2. So lambda by 2, lambda by t, sorry, and lambda equal to dt. Okay, and if we put here and we solve, here we find that sine 2 pi t by t. Okay, sine 2 pi t by lambda is sine 2 pi t by t. And if we solve it, we will find that, and if we put here the values, okay, sine 2 pi t by 0, and if we solve, okay, now important one is that particles in this case are passing through their extreme positions and they are supposed to be stationary. Why? Because their velocity is 0. From equation 5 you will find that velocity is 0. If we put sine function 0, then velocity is 0 and displacement and strain is maximum. Okay, so when the velocity particle of the particle performing SHM, when the velocity of the particle performing SHM is 0, when it is at the, what you say, its extreme position, at the two extreme position. That means the particles are now at their extreme positions and they are stationary at the instant. Okay, now how these instants can be obtained? Okay, so the sine function is 0 and sine function is 0, that means it is multiples of pi, and that will be equal to m pi. And if we put here, if we solve here, the value mt by 2 will be there. Okay, and stationary events are 0, t by 2, t, 3t by 2, 2t, etc. etc. So stationary events. These stationary events, when we are going from 0 to t, these two stationary events are occur. Uh, so occur twice in a period. Now exactly reverse situation is there where we consider cosine function as 0, and after substitution in equation 3, 4 and 5, we'll find that the velocity is, from equation 5, the velocity is maximum while displacement and strain are 0. And when the velocity of a particle performing SHM is maximum, when it is at its mean position. That means particle are at mean position or normal positions for these stationary events. And these stationary events can be equated by equating the cosine function to 0. And in this way, we find it is odd multiples of pi. So it will be 2m plus 1 t by 4, t by 4. So t by 4, 3t by 4, 5t by 4. These will be the different instants. Again, these instants are repeated twice, but the initial instant, in the previous case, the instant was started from 0, and in this case, it has started from t by 4. So these stationary events are started t by 4 later than the previous events. Okay, and the session is open for the questions if any.